Okay, so
Wow.
looks like you've all mastered folding, which I'm very excited about. Okay, so no takeaways, no notes for today, so no takeaways. We're pausing. Today is a day to kind of work with all of the derivative rules. Okay, so eventually we'll get into our note packet, and it's on page 20. But basically, our essential question is, as I write it on the board, so realize I erased. They got distracted. How can I organize? Oh, can I organize all the derivative rules? You want something that we can go back to from now until the end of the year. So I think you've all probably beat me to this, right? We look for the highest number, that's a 5. Put that down. Then we look for the 4. Put that down, and then 3. Put that down. Right, then we just start folding them over. So we got the blue, then the green, then the orange, then the green, excuse me. And then when you fold over the green, you see 2. Fold over the orange, you see the 1. The blue, you see the double. Right? Yeah, something that looks like this. Okay, staplers. You know, I usually staple the crease, right? I open it back up again. I should just be able to slide right in. I think it's short enough to do that. Yep, it is. Hit the crease. So I'm going to send the staplers through. Put our staples in there, though.
Oh, I was about to say.
Yeah. It'll snap your finger off right now.
Yo, I stapled my thumb once.
Oh, that's not good.
It was a fun experience.
That is not good at all.
And fun will start.
That is definitely not. Okay. Not sure what that is. There we go. There we go. Okay, so we begin with rule 1. I have a blast from the past. And these are just, these are just our properties, right? We have properties in math that allow us to add and subtract and multiply and divide, right? And we have the same derivative rules. You can actually put a plus minus on these things here. You can actually put plus minus and plus minus. But you have these written on the side, right? So we're going to not only give you the rule, but give you an example. So we are taking the derivative of 3 times the quantity x squared plus 2. I could have distributed the 3 and just taken the derivative, right? Or you could look at it as 3 times the derivative of x squared plus 2, which is 3 times 2x, which is 6x. Okay, so you should have the problem, right, sitting there. Does that make sense? Does anybody need a pen or a pencil? Are we all good? Okay. Okay, so if I have 2 terms added together, I just take the derivative of each term. So we got our 6x plus 4. I know this is really kind of formal, it's kind of something you do intuitively for those 2 problems, but those are technically the properties. Okay, then we get into our product and our quotient rule, product and our quotient rule, right? So we multiply those 2 things together, then we get u times the derivative of v, so this times negative 2x, plus derivative of this, which is 2 times this. And I just put it in the order that they wrote it here. See how they kind of wrote it backwards? We're used to seeing it as uv prime plus u prime v, right? That's how That's how we have the, we always keep the U's and the V's in the same order. But there's, I mean, it's a sum, so there's lots of ways to write that, sum and a product. Okay, and this is our low D high minus high D low. So here's our high and our low. So our low is x squared, our D high is 2, minus our high is 2x plus 1, our D low is 2x. And then squaring the bottom, remember how I always say don't touch the bottom, right? We square something, yeah, it didn't sound good. You square something like if you had x squared plus 7, you wouldn't want to FOIL it. But as long as you just have x squared squared, go ahead and write that as x to the 4th. When we have a monomial down there, we do simplify. Am I going too fast? Scream if I'm going too fast. I'm just going to give this to you simplified. There's a lot we could do with that. We could still factor out a -2. Does that make sense? We could still factor out an x. Does that make sense? And if we do, we can cancel with 1 in the denominator. So, oops, I'm sorry. So there's a step here that probably is worth going through. So you might want to take that into that last step. Okay. So derivative of a constant is 0, right? A constant is graphed as a horizontal line, like y equals 7, or y equals e. That would be at about 2.7. So derivative of 3 is 0. Horizontal line at 3 is 0. Okay, your basic, these are ones with chain rules now. Your basic chain rule, or your basic power rule with a chain, right? So that's our chain rule out here, right? The outside is the power and the inside is the u, which is a function of a different variable x. All right, u is a function of x. That's why our Leibniz notation has the x in the bottom, but we see this u that we're taking the derivative of. So like this, right? Our power is 7 and our u is 2x cubed plus 4. So we do the power rule, 7 times all that stuff to the 6th times 6x squared. And then we simplify, we get 42x squared out front with all that stuff to the 6th. Am I going too fast yet? Huh. I don't know why it says 1:55 a.m. That's weird. I'm pretty sure it's not 1:55 a.m. Sleeping. Okay. Rule 7 is just differentiating x. If we graphed y equals x, it would be a straight line with slope of 1, right? mx plus b with b 0. So a slope of 1, so the derivative must be 1, right? That's the coefficient in front of the x. 1x. So if I take the derivative of 4x, what's that? 4, right? It's just a line with slope 4 and intercept 0. I say slope, you think? I haven't said that in a while. Okay. This is also a derivative of an x to the first power, but we can rewrite it as like that, right? Derivative of 1/3 x, but a lot of times we see it as x over 3. So this derivative then is just what? 1/3, exactly, right? It's this line with slope up 1, right 3, up 1, right 3. It's just kind of flat. I say slope, you think, yeah. 8 absolute value We don't really see it ever, so don't worry about it. I haven't seen that on a test in a long, long time. Of course, now that I said that,
Thank you for knocking on.
right.
That's not even.
Ah, dang it. There you go. Yeah, now that I said that, honestly, if it shows up, it'll be one multiple choice question. So put it in perspective. That's more important things to worry about. Okay. 9. So we have the trig rules. They are right here, right? But these trig rules don't contain the chain rule because the variable inside the sine function is x and I'm differentiating it. Okay. So these will contain the chain rule. They're a little more universal, right? So if we take the derivative of sine of u, it's cosine of u, but then we have to do the derivative of the inside, which is function u. So it would be something like that, right? The derivative of the sine of 4x cubed is cosine of 4x cubed times 12x squared. Right? There's that chain rule out there. I think I leave it with 4x cubed all the time, right? So if I do this one, it's going to be minus sine of 4x cubed times 12x squared. Good, okay? Secant would be, excuse me, derivative of tangent would be secant squared. So this would be secant squared 4x cubed times 12x squared. Same chain rule, right? Same u. So the chain rule is the same in all of these because the u is the same in all of them. You doing okay so far? Am I going too fast? All right, let me know if I am. I tend to, talk faster than people can write, so slow me down. All right, let's go through the other 3. So if we have secant of 4x cubed, it's going to be secant 4x cubed tan 4x cubed times that same chain rule, 12x squared. So these are really popular with multiple choice questions. All right, we're going to sneak that chain rule everywhere we can. So cosecant, it's a co-function, so we must have a negative derivative. So negative cosecant 4x cubed times cotangent 4x cubed times 12x squared. Our last trig function, cotangent 4x cubed, co-function, negative derivative, negative cosecant squared 4x cubed times 12x squared. So far, so good. I'm going to leave it on that page for just a second. You still see pencils going, so okay. Oh yeah, what's up, Miranda? Sure. Can I go? Is it okay if if I go back? That one? Oh, good. Okay. Sorry about that. I did race through that page. Okay. So all of our first trig functions, right? All of these. Now these we do have these. We do have the chain rule. So they are up on the board. Arc means inverse, right? We can either write it sine. Arc sine means the same thing. And you'll see that right in the directions on the AP test. Okay, is that they'll explicitly tell you those 2 notations are equivalent. So just be ready to use them interchangeably. And did I stick with the 4x cubed here too? I did. Yay. All of that is written for you, right? So we can just start differentiating. So all we're doing is we're saying, hey, the stuff in the brackets is the u. We're going to stick it where I see u, and then we're going to differentiate it and stick it either in the numerator or off to the side there. So this is the square root one. So it's just, I have to square this at 16x to the 6th. And then I'm going to multiply it by 12x squared. So all of these have a u squared in the denominator of some sorts. So squaring 4x cubed is 16x to the 6th. So you're going to put 16x to the 6th everywhere. And notice I started sliding the chain rule up into the numerator. So if you didn't catch that, started out like this, and then I slid that chain rule up into the numerator. That's how you would see it on a multiple choice. And then we get to the arcsecant and cosecants, which are a little not fun. Notice they didn't do all the cos on one side and the not co on the other side. It makes it a little harder. I think it makes it harder to navigate. I didn't make this. Put all the cos on the right because they're all negative. Now the non-cos. So they're slightly rearranged from what we typically would list them down as. Oops, do you want me to go back? Get too fast, sorry. I looked up and I saw pencil still going. Sorry about that. Can I go on? Is that okay? All right. So getting into the exponential and the logarithmic. First of all, we're going the LOG we're going to get rid of. Okay. And so this is the way the chain rule can show up. X in the exponential, it's always going to be in the power up here. So anytime you do the derivative of an e, it's itself. We always end up with the same thing. Then we just differentiate the power. Even if the base is not e, same pattern. It's a exponential. It's something to a variable power. So we get itself. Oh, I rearranged that. Sorry about that. We get itself. And then we need just the natural log of 7, right? We'd have a natural log of e up here, but it's just 1. And then we do the chain rule. And boy, it's kind of a crapshoot as to how this shows up, but usually the 12x squared shows up out front. You know, it might be something like that. They might keep the natural log on the right hand, over on the other side of 7 to the power of 4x cubed. And then our natural log is just a reciprocal of whatever we see in the bracket. So it's a reciprocal of that times the derivative of that. And that's worth simplifying. We've got a lot of canceling going on here. So I'm going to write it as a top-bottom fraction. We can see that we simplify the coefficients to a 3 on the top. And everything goes away except the x on the bottom. Yeah, it ends up being 3 over x. It's an interesting pattern. If you do enough of these, there is a pattern there. I don't want to harp on it, but there is totally a pattern to differentiating L and U. Like sometimes you can see where the 3 comes from and where the why it's always over X. In other words, we lose all the power on the bottom. Okay, log is out. Obviously, those are for forests. This is just we've differentiated this a ton of times, right? It's u to the half power, so it's half u to the negative half power du dx. Okay, so if we did something like the square root of 4x cubed, we bring down the half 4x cubed to the negative half times 12x squared. And this one is also worth simplifying. So I'm going to write it as a top bottom fraction. Oh, that's inconvenient. Hold on. There we go. 12x squared over 2 times this to the half, which is this, right? This to the half is square root of 4x cubed. 12 divided by 2 is 6. And square root of x cubed can actually be simplified, right? We can bring an x squared out as an x. So it ends up being that. Yeah. So that's why I said this is worth simplifying. The 2 and the 6 reduced to a 3 on the top. So we have 3x on the top over root x on the bottom. And just when you think you're done, you're not, because x on the top is really root x times root x. So we get a root x canceling, and we get 3 root x. Holy cow. That's all I got to say about that. There's pattern there too. It's just harder to see. Like I said, I wouldn't get caught up in the patterns, but definitely worth simplifying natural log when you differentiate that, and anything to the half power. Lots of simplifying going on there. Do we have any questions so far? Oh, now the 1:20 whatever a.m. made more sense. My camera. That was in the PowerPoint. Y'all good with the writing? Yep, I'm not going. So now, when can we use the flip books? Always. When can we not use them? Just the AP test. But yeah, but then you won't need them. And just another plug for the AP exam. You guys are doing great. You're staying current, which is awesome. That's the key to success. You all should feel very, very capable of taking that AP test in May. Okay, so to put this in perspective, oopsies. We did the flip book. We're done with that activity. You have topic questions in College Board. Some of you still have to do topic questions from day 7 as well. But this week is kind of a week that's really dedicated to topic questions. So if you're behind by a day or so, don't worry about it. Tomorrow we have some really basic stuff, and same with, or not tomorrow, Wednesday, same with Thursday. So we got time to catch up. So with the time you have left today, decide if you want to jump into topic questions right now or con. I don't care, either one. Just know that whatever you don't do in class right now, you should be looking at doing either tonight or in class on Wednesday. Okie dokie. I'll be around to check in with you.